Over the next couple of videos, we're going to be looking at an example of a mobile phone network. And so this is represented in our diagrams below. So first, we can see here on the left, we have our very well drawn little person with his or her nice cell phone there. And they're sending some signal, maybe they're calling, they're sending a text. And that signal is going along this blue line, this uplink through free space. And it's reaching an antenna, which is on top of some tower. So after this base station antenna, the signal is going to some low noise amplifier. The signal then goes through some cabling to the bottom of the tower where it is fed into a receiver, and then it can be sent out to wherever it needs to go. So here we have a diagram that is more similar to what we've seen before in this lecture series. Notice there are a couple components missing just because they're not necessarily relevant here. In a real system, for instance, we would still have a modulator on our transmission side and a demodulator on our receiver side. But we see here that we have our input signal with some power, transmitted power piece of T. We have a transmitting antenna, and it has some gain, and we're going to talk about that in just a second. We have some free space loss, this L sub s. So as we're transmitting the signal along this uplink path in blue, we are losing some portion of our power. We have our receiving antenna with some gain again, and we'll talk about that in a second, as well as some ambient temperature. We then, after we receive the signal at this receiving antenna, we have some power of our received signal. It goes through this preamp, our low noise amplifier. So up here's our low noise amplifier, and that's represented in this diagram below with an amplifier with a gain of G amp and an effective input temperature of T amp. Our cabling between the receiver and our low noise amplifier, we can represent it that it has some losses by sort of this vertical resistor symbol here. And we note that we have some loss ratio LC, and we can also correspond that or correlate that to some effective input temperature T sub C. And so then the signal is going into our receiver. And so at our receiver, something that we're going to be interested in is we can say at this point, our signal has some power for the signal. So power of the signal at the receiver, we'll call it P sub SR, as well as some power of noise at the receiver. And of course, ultimately what we're going to be interested in is the signal to noise ratio. So ultimately we're going to be looking at the power of the signal at the receiver related to the power at the noise at the receiver. And so we'll get to that in our subsequent video. So first, let's come back and let's look at this idea of antenna gain. So we said these antennas have some gain. So I just want to define that, and then we'll mention a couple other sort of ideal approximations we're making. We'll sort of set up the problem, give some parameters, and then we'll actually solve the problem in our next video. Okay, so our antenna gain is basically just the amount that our antenna can increase the radiation compared to an isotropic antenna. So the amount by which an antenna increases radiation in a given direction and so of course there's going to be some preferred direction where we want to be sending our signal over the isotropic case. And so we've not seen that word isotropic before, but we have seen, I've mentioned a type of antenna called omnidirectional, and so that's the same thing. So omnidirectional. And so basically what we're saying is if we compare to some antenna, so maybe we have some antenna that looks like this, and it radiates in all directions. So it has signal going in every direction. So this would be our omnidirectional or our isotropic. So now maybe if we have some other type of antenna where we've created it such that it's only transmitting in a certain direction, so maybe we have the same amount of power, but now all of that power is being sent in sort of one direction. So the amount of power or sort of the amount of radiation in this region compared to the same region for this isotropic would be our antenna gain. So it's important to note that our antenna gain isn't actually amplifying the signal the same way that we talk about, for instance, this G amp amplifying the signal. So important distinction there. So it's best to sort of think about this antenna gain and our amplifier gain as sort of two separate things. So now let's talk about the two antenna gains that we would have in this problem, one for our mobile phone itself and one for the antenna that's on top of this tower. So typically our mobile phones are going to be isotropic. So they're just sending that signal in all directions because you don't necessarily know where the closest mobile network, the closest antenna is going to be. So typically this will be isotropic. And so what that means is we're going to say that this gain of our transmitting antenna for this problem, let me clean that up, we're going to say that that's just equal to 1. Or if we wanted to have it in dB, we can say, of course, that's just going to be 0 dB because log base 10 of 1 is 0. Now, our receiving antenna is going to have some gain. So our receiving antenna, and so the reason it's going to have gain is it's going to be more sensitive to signals coming from or right below the horizon. And so, of course, that makes sense because not many people are going to be using their cell phones when they're above an antenna that's mounted on a tower. So more sensitive to radiation or signals from our phone at directions near and slightly below. Just give me all kinds of trouble today, apologize for that. So near and below our horizon. And again, that's just because we're not going to have people calling to use these antennas when they're above them most of the time. So our gain for our receiving antenna is going to be greater than 1, or in terms of dB, greater than 0 decibels. Okay, so a couple other things about the system. We talked a little bit about our cabling, our LC and our TC, which represents loss and noise respectively of that coaxial cable. So I didn't mention that it's coaxial, but typically this cable here will be a coaxial cable. And so we'll talk about that a little more in later classes. But for now, we'll just worry about the loss and effective input temperature, LC and TC. A couple of things also to note about sort of this uplink part is that for this diagram, we've shown a direct line of sight between the phone and the receiver. So typically, we don't have that. That's not going to be the case. So let me just say our diagram shows direct line of sight between phone and antenna. And so oftentimes this is not the case. So let me clarify that with often not the case. And so typically the reason that's not the case is, of course, if you just look around you and consider you're going to make a phone call or send a text, you'll of course see you have buildings, trees, various things that can interfere with the signal. So typically what we're going to have is we're going to have more energy lost due to scattering and absorption in sort of the environment. So more energy lost as our signal is scattered, absorbed, reflected, basically as it's interacting with the environment. So if we really wanted to know how to understand these losses, we'd have to look into something called radio propagation. But that's an entirely different thing. So again, with this unit, a lot of what we're doing is just sort of introducing these ideas. But if we wanted to know better about this, we could study radio propagation and determine more approximately what these losses are. Sort of as a point for comparison that we'll come back to after we work this problem, we can consider the simplest case of the signal propagating in free space. So simplest case, which is going to be propagation in free space. So we don't have any buildings, trees, anything like that that's going to interfere with this signal. So our loss, and we're going to put subscript fs to indicate this is free space, is equal to 4 pi r divided by lambda, and that whole quantity squared. And as we've said before, our lambda is going to be equal to the speed of the wave. If we're in free space, it's the speed of light, c, divided by our frequency. So what we see from this is that the loss goes as the distance from our source squared. So r would be the distance from our source. And we see we also have some frequency dependence. So as our frequency gets larger, our loss is getting larger as well. So we can kind of use that again as sort of a first approximation. After we have our solution, we can come back and we can say, in our best case scenario, how much loss do we have? Okay, so after talking about all of these qualifier things, we're ready to sort of state our goal for this example, and then I'm going to give some values, and then in the next video we're going to go back and we're going to work through this. So our goal is, here in a minute, I'm going to give some specifications for that system that we drew above. So we're going to say, knowing the specifications for our transmitter and receiver, what we're going to do is we're going to specify our maximum allowable loss. So for transmitter and receiver, we want to determine maximum, just not playing nice today. All right, maximum acceptable propagation loss, which is our L sub s. And we want to find basically the maximum L sub s that we can have and still have the system operate. So keep in mind, if we had a better understanding of this radio propagation, what we could do is we could say, well, in a given environment, that means we have to be so close to our antenna. Or we could also say we have to have a certain frequency for a certain distance. But again, we're not going to get into that. We're going to sort of ignore that. And then at the very end, we can come back and relate it to the simplest case of free space. But just, again, keep in the back of your mind, if we knew more about radio propagation, we could ultimately transform this maximum acceptable LS into a maximum distance in a given environment at a given frequency. Okay, so the last thing we're going to do in this video is present some known information about our system. So let's start with our transmitter side. So for our transmitter, we're told that we have power in our transmitter is equal to 250 milliwatts. And so we know that this power isn't going to be very large because, of course, this is coming from a cell phone. So every time we're sending a signal or sending a message, we don't want to be spending a large amount of power. The gain of our transmitting antenna, as we said before, is just going to be 1. So 0 dB. And the frequency, which is going to be a common frequency for mobile phones, is 2.4 gigahertz. Okay, so now our receiver antenna, let's specify the operation of that. So receiver antenna. For our receiver antenna, we have an antenna gain of 63. So remember, we expected that to be greater than 1 because it's only looking sort of below the horizon. It's not looking above where it is. And we also have an ambient temperature of T sub Ra. Let's just assume it's approximately room temperature, 290 Kelvin. And so again, this is, I don't think I wrote it explicitly earlier, but I mentioned it. So this is just our ambient temperature where our antenna is. Okay, so now let's specify our receiver amplifier. So our receiver amp, so this would be our low noise amplifier coming right after our antenna. So we have the gain of our amp is 15 dB. And we have that the noise figure for our amplifier, F in dB, is equal to 2 decibels. Our receiver cabling so remember, we're going to have some loss in this cabling, and so in the homework you're going to look at how switching the order of this our L and A and our cabling can drastically affect operation. So our receiver cabling, we have that our loss ratio L sub C is equal to 3 decibels. And we just have some ambient temperature, which as we had defined it before was TA, so ambient temp TA, which is equal to also 290 Kelvin. And then so finally, we need requirements for our receiver. And so basically these are going to be minimum requirements that our receiver has to meet in order to still operate. So we're saying that our minimum signal to noise ratio is equal to -7 decibels. And that's in a bandwidth of 360 kilohertz. Okay, so I know that was sort of a lot of work to set up this problem. We're going to come back in the next video. We're going to review sort of these given specifications, and then we're going to work through our problem.